Well, welcome back to part 3, a riveting installment of my journey of prime densities using the golden ratio. Ignore the things on my thumb here. I got in a little fight with my cat. You don't need to watch the first 2 parts to understand this video. All you need to know is that I came across this equation recently, and I didn't understand why it worked or what it really was. It just was really good at predicting primes. How many primes? So yeah, in this video, I'm gonna break this down and figure out what it is. And actually, when I did so, I actually came up with a very intuitive reason of what's might be going on here. And I'll explain that too. So yeah, it turns out that all this equation really is doing is giving another constant besides -1 of x over ln of x. And it's this constant, which is equal to 2 minus ln of the golden ratio plus 1. I'm not sure how I figured out that that's what it was, but that's what it is. So yeah, it's not too exciting actually, because this has been done before. Legendre thought this. He thought it was 1.0836, I believed. Yeah, so these things have been thought of before. Unfortunately, his was found to be too high because it's believed that it tends towards just -1. I don't think that's been proven. It just seems like it from data. So yeah, by those standards, mine's more accurate than Legendre, so it's a win for me. But it's still not proven that this is right. It could just go to -1. So yeah, so let's break down this equation, just figure out what is going on here. So first of all, let's just take out the golden ratio. And if we do that, it actually, this just equals that, ln of x. So yeah, this is all just junk, actually. I was pretty cool and disappointed at the same time. So let's just stick with this. Let's get rid of all this mess and just stick with x over ln of x. And let's plug back in the golden ratio. And when we do that, we find some interesting things, just like most things with the golden ratio, that the golden ratio over ln over the golden ratio is equal to negative golden ratio over ln of the golden ratio minus 1. Just another strange property. And that also equals the golden ratio over ln of the golden ratio plus 1 times 2. You could plug these in and you'll get the same answer for all 3. And that's only for the golden ratio. You can't put in any other number and it will do that. So yeah, then it got me thinking, maybe the problem with E and why it always just doesn't give the exact measurements of one is that we're not breaking down E enough. And let me explain that here. So what I believe about the number E is that we found it from working up, down. Like we always break it down to get to 2.7. We never work from 0 up to E. And by doing so, we have a very, what word do you want to use? Digital or binary way of looking at it. We have 1 right here, your length 1, and then after 1 unit of time or whatever, it doubles, obviously, and then there's 0.718 left. All right. But the problem with that is that these lines aren't accurate. They're not here. 1 didn't double. I mean, it actually grew from here an infinite amount of times, and that's how it should grow. Almost like you have to break up E more. And of course, the golden ratio is perfect for that, because the golden ratio is a spectrum. It can divide anything, and E really can't. We need to break this down more. And so obviously I just took it, E, and I divided it by the golden ratio, 1.67. And you can see it's already starting to look a lot more like the way it should. 1 grew. And then, I took this area and divided it up by the golden ratio, and I got another length. And in doing so, I came across this pretty cool equation here, which can be broken down into that. It looks even better if I write it like that. Now, So obviously I didn't know if this was right, so I decided to break it up, see how many ways I could break it up with a golden ratio. And, well, I found an infinite amount of ways, really. Yeah, you could break it up into as many fractions as you want. And I can't believe how cool this is. I've seen every video and seminar on the golden ratio. I have never seen that. I don't know why. Yeah, it's got all the negatives, and all the positives at the end. So you could have as many fractions as you want. You can divide any number as many times as you want. But yeah, I wanted to look at how to do it for e, and that is when I came across this one. So e divided by the golden ratio squared, if you start with that one, you'll get every power after that, and this tends to 1. I'm not sure if it does, but I've written a lot of numbers and it seems to go to 1. Okay, and now we have a beautiful way of looking at e now. Okay, so as 1 grew to 2.718, 1 is no longer 1 anymore. It is now 1.3829, which is e over the golden ratio squared. The next segment is 1 over e over the golden ratio cubed to a fourth, etc., all the way to infinity. This is how growth happens, not in these discrete chunks that we believe. And this is why -1 is always underestimating, at least at first. I'm not sure how it gets bigger and bigger. Maybe 1 gets smaller and smaller eventually, but that could be the answer instead of -1. So yeah, we're left with this equation. Now, yeah, you put this in and you'll get great guesstimates for the prime density. Now, the only problem with this constant that we've created is that, like Legendre, it may still tend to 1. So it could be wrong, it could be right, I don't know. I can only calculate so high with Desmos. But that is why I introduced this exponent. This has a couple of purposes. First of all, it binds it to ln of x. So the higher ln of x gets, the lower this all gets here. So it will tend to -1. The other great advantage of this is that you can almost see it as like a fine tuner to this equation. You can change these numbers around, the y and the x a little bit. You can make this squared, you can put the -1 here, you can make this the y 50. You can do a bunch of things here to make it really close to the actual numbers. And yeah, you see it like a little fine tuner. So this is like your starting point, and this is what you use to bring the number down or make it more accurate. So let me go to the calculator here and show you some examples. So here's just a few examples you can see from the equation that you can use. Here's ln of x minus 1 for reference. And here's the actual thing that I've created. And as you see, as I add more zeros, it tends towards 1, which is what we want. So yeah, you can see here's just 1 over ln of x minus 1. That works pretty well. You could even multiply this thing to ln of x, and I did find some good combinations, but I lost them. So yeah, here's 27 over ln of x, which works really well, and I'll show you some calculations of that. But yeah, they all tend to go over the amount of primes, but if we put the exponent at 0.5 of ln of x, it actually seems to stay below, and it works really well with 13, and I'll show you those calculations now. So I strongly urge you to plug in this formula and just play around with these numbers and see what you come up with, and see maybe there's a perfect combination that we can find. I'm just going to show you a couple of the ones I've found that seem to work really well. First, I mentioned the one with 27 in it, and of course, being the kind of person I am, I try to find constants that added up to 27, and I came across this one, golden ratio cubed, e cubed plus pi cubed divided by 2, which is actually 27.66. Yeah, and then I obviously plugged it in and checked, and it's actually way better than just 27. I'll show you some numbers here. 10 to the 29. There is what the answer is. There's what that gives you. It's super close. Bunch of 9s. ln minus 1 is a lot further away, as you can see. 10 to the 100, I have to use Li now. I can't find a higher prime anymore. Yeah, you can see it does go over, but it's still really close. So it could be an upper bound. Like I said, I do not have access to a supercomputer. If one of you just randomly do, can you please start putting this equation and looking into this? Yeah, down here you can see 10 to the 200, still super close, a lot closer than ln minus 1. And here's 10 to the 300, still nice and close. But like I said, it does go over. So once again, we can play around with this equation to keep it under. And it seems that if I raise the x to a half, it seems to stay under. So this makes it go to 1 faster. I don't know, that might be an actual number. But that works really well with 13. I haven't found any constants to make up the 13 to make it better, but it seems to work really well. Here are some examples. You can see it's a little further away than the other one, only 4 9s, such a disappointment. But as we get higher, it gets closer and closer, and it doesn't seem to go over at any point. Actually, I did find 40 over 3 with 13.33, which is incredibly close, and the first few digits right here are exactly the same, and it's 0.999, I don't even know. So maybe that's the constant. Like I said, play around with it and let me know what you come up with. Thank you. Bye.